So I mentioned in Slack that I think people have written papers about clustering breast cancer data, and there's actually a lot more than I expected. I think because people know there are subtypes of breast cancer, so it's like an interesting example to try to cluster. I can't recommend a particular one, but I thought this was cool. Okay. You can see my GitHub tab, right?
Yep. I can see it at least.
Okay, cool. Oops. Didn't like that I moved my window. All right. Okay, so next we're going to give an overview of deep learning, which is a technique within machine learning. So you can think of the stuff that Taylor just presented as statistical learning, or you can call it machine learning if you want. And deep learning is a technique within that. And at least working at ALCF, this is what we're seeing a lot of, is if people want to do machine learning, they tend to want to do deep learning. And I think that's because it tends to outperform other techniques in the context of having a lot of data. And so like Taylor said, we're just doing like a quick overview, partially to like intrigue you into maybe using this, learning more and using it for your scientific applications, but also so that this afternoon we can talk about scaling in the context of machine learning. And I know some of you might already know this stuff, so I linked here to one of our other repos, like Taylor mentioned, if you want to like use some of our other tutorials that are maybe more advanced and take advantage of us being around to ask questions. And then for later, if you want like a more thorough introduction, I really like this book that I linked to here. I actually have it on my desk next to me. This hands-on machine learning book. It uses scikit-learn, which is a very common Python library for machine learning, and it uses Keras and TensorFlow, which we're going to talk about today. And it's really nice for being able to like try stuff out as you go along in Python, and they even have a whole repo of notebooks so that you can try the examples in the book. Okay, so to keep this scoped, we're going to specifically talk about a supervised learning problem. So that means, unlike clustering, you have labels for all of your data. And specifically, this is classification, meaning that the label is some class, not like a real number, but categories. And specifically, we're going to talk about classifying handwritten digits as the numbers 0 through 9. So this is like a real early success of machine learning. So if you think of like the post office wanting to sort your mail by zip code automatically, then you need your machine to read everyone's handwriting. And this data set is freely available. It has tens of thousands of examples of handwritten numbers. And for each image, we have the label, the digit 0 through 9. And so we can represent the image as a matrix of numbers. And in this machine learning task, we want to learn some function that will map the image to its label 0 through 9. And this is like a common introductory example for machine learning. First, we're going to go through an introductory notebook that builds up the ideas of neural networks sort of by hand. Then we're going to talk about how to use the Python package TensorFlow, which has the Keras API within it, so that we can do more complicated networks without doing everything by hand. Then we're going to introduce convolutional layers. And then if we have more time, we can experiment with how to improve. And we're going to talk about this more later, but it's very important that you hold out some test data. So this will come up in the notebooks. Okay. So if you go back to your collab, you can go to our repo. Again. And we're starting with this introduction MNIST. So I already opened it in this tab. And we're going to look at how to fit this function for this MNIST data set that will map an image to the label 0 through 9. So again, we import some helpful Python function packages. And then MNIST is so common that TensorFlow actually built in a way to load the data. And common naming is that the input to your machine learning is X and the output is Y. So just like is common when you learned about functions in like high school, f of X equals Y. And they already have the data split between train and test. So the training data is what we actually use to fit the function, and the testing data we hold out. We do not show it to the machine learning, and then we can use it to check the error on this held out data and see how well our function generalizes. So we load up the data. Say we want it to be float 32. Here we're normalizing. We know that the biggest entry is 255. We're going to divide by that. So all the entries are 0 to 1. This tends to help with machine learning, including neural networks. Here we're reshaping the data for this particular example. We are flattening each image into a vector. The labels are just 0 through 9, so we might as well make them integers. And here we print out the sizes. So the training data has 60,000 example images, and each column is a flattened image, and it's of length 784 because the images were 28 by 28 pixels. And then here we can look at what the data looks like. Here we showed the first 10. So as you might expect, they're just little black and white images of handwritten numbers. And we can see some natural variation, like some people write their 4s like this, and some write it like this. And people have sometimes sloppy handwriting like this 5. And first, we're going to do linear regression to kind of, so this is a little bit of a repeat of what Taylor talked about, but kind of in this context of this data set. So one difference is this morning, Taylor's inputs were one-dimensional, so we just need to learn a slope. Now our inputs are a vector for the flattened image. And so instead we're learning a whole vector. So it's like really a dot product. And we're going to consider multiple examples at once. So our input images are a matrix where each row is a flattened image. So to apply this linear model, we're going to do data times A. And I know this is backwards. Normally people put A times X, but it's convenient for neural networks. And then again, our error is going to be mean squared error. This is common. So we have the true labels 0 through 9. The predictions are linear model output. Square the errors and take the average. And then this function does one step of the gradient descent. So we feed in our current guess at A and apply the linear model, and then we calculate the gradient. And if you write out the vector calculus, this is what you get for the gradient. and then you update A. So you had your current guess minus the learning rate times the gradient. So this is very similar to what Taylor showed, except now we have higher dimensions. And in practice, it can be computationally expensive to calculate these gradients on all of your examples at once. So we often look at just a subset, just a batch. And this is, you can think of this as estimating the gradient, because in the gradient, we're averaging over all of your examples. So if you look at a subset of your examples and average over those, that's an estimate of what you would have gotten if you used all the data at once. And using a batch, it's not just making each step faster, it also inserts some noise because you're just estimating this gradient, and that's both good and bad. And we'll talk more about that. And at the moment, we're doing the simple thing, which is just take a fixed batch, but really you'd want to take a random batch for each step. So here we have the loop over 5,000 iterations. We keep updating A using gradient descent, and we calculate the loss at each step. And so you can plot this and see, okay, it steeply decreases, there steeply decreases, it starts to flatten out. If we thought this was promising, we might run this longer because maybe it's going to get better. But we can stop here and see how it's going. So here we show the first 10 examples again, but they're labeled with the output of this linear model. And as you might expect, this is really not working well. We wouldn't really expect it to work well because we're inputting all these pixels and we're just multiplying by this vector, and we think it's going to output the label 0 through 9. In this case, it even output something negative, so that's really not working. So if we think about how to improve it, one thing would be add a bias term. So matrix multiplication plus a vector. So you could call this, instead of a linear transformation, an affine transformation. So I'll use that phrase later. You could also reformulate it as a classification. So right now it's outputting these real numbers, and we're just interested in numbers, integers 0 through 9. So this is similar to like going from linear regression to logistic regression. And we could also choose some error other than mean squared error. So let's dive into that a little bit more. In logistic regression, you have this sigmoid function, and it's shaped just to output things from 0 to 1 and mostly 0 and 1. So you could say, oh, let's do the affine transformation, multiply by A and add B, and then apply sigmoid. But we have 10 classes. We don't just have a binary problem with 2 options, we have 10 options. And so one approach is to use this one-hot encoding, and I'll show you what that looks like. Instead of the label of the image, of this image just being the number 5, the label is this length 10 vector. It's all zeros except 1 in the index 5 spot. So similarly, class 0 has a 1 in the 0th index. And so you can imagine you could have, instead of sigmoid at the end, this thing called softmax, which is similar in that it forces outputs from 0 to 1, but it also forces them to sum to 1, so it's like a probability distribution. So the output of our function will be this 10-dimensional vector with entries 0 to 1, and you can think of it as like probability that each class is the right one for this image. And then, as I mentioned, you might not want mean squared error. It's common to instead use something like categorical cross entropy, and I'm not going to dive into that since it's since we're just doing like a quick intro to deep learning, but you can read more about it here. Okay, so we could try all of this and calculate those gradients, and it's not going to work very well on these images. So now we're building up this motivation to have neural networks. A neural network you can think of as having multiple layers, where the basic layer is this affine transformation multiplied by a matrix and add a vector, and then you have a nonlinearity. And here I wrote sigma, which people often use for sigmoid, but it doesn't have to be that function. So this would be one layer, but we could do that again. I should stop. Okay. So with two layers, it'd be like you do that, then multiply by another matrix, add another vector, and apply a nonlinearity again. And people often draw this as a network. So here, this first column of nodes is your input to your function. And here it's drawn as a three-dimensional input. And you multiply by this matrix A1, like we wrote here. In this picture, the matrix is 3 by 5. So that output is this 5-dimensional column here represented by 5 nodes. And then you multiply by A2, which would 5 by 2 in this picture. And so your output of this function is 2-dimensional. So this is just some arbitrary sizes to draw here. And if you wrote this like in Python, it'd be something like this. So you do your affine transformation and apply your nonlinearity. Then do it again. Another affine transformation, and then another nonlinearity. This is, you could think of this as a 2-layer neural network, but people also say it has one hidden layer. So one layer that's in between the input and the output. And we could go further. We could add another layer. So do another affine transformation by multiplying by A3 and adding B3 and applying another nonlinearity. And this would be drawn like this. So we multiply by A1 to get here, multiply by A2, multiply by A3. People usually don't draw in the fact that you're adding these biases, these vectors, because that just like clutters up the picture more. And if you were going to write this down in Python, you could write it like this. And as I mentioned, the nonlinearity doesn't have to be sigmoid. That was kind of the, I think, original idea. Here are some examples of other activation functions people use. And one popular one is ReLU, this one right here, which is max 0x. That basically means all the negatives get sent to 0 and the positives get passed through. Okay, so neural networks have been around for decades. They got more popular more recently, like 10, 15 years ago, because they started working better. And so you have, especially like after 2012 or so, we have better hardware. The methods got a little better. We have bigger data sets and so forth. And one thing that people found is that it's helpful to have many layers. And so this is called deep if you had a lot of layers here. And that's why people often call this deep learning. So if you hear deep learning or you hear neural networks, I think of it as the same thing. And so why do people like deep learning? Well, one thing you can think of it in the like basic usage. In the basic usage, you're learning a function to map your input to your output. And so you can think of this as a nonlinear function fitting. And the hierarchical structure of a neural network requires fewer parameters than other ways to fit a function, like polynomial regression. Like if you just said, I'm going to have all these pixels from my images and fit some like complicated polynomial in order to output these labels. Also, there's different variants of this universal approximation theorem that roughly says there exist neural networks to approximate any nice, smooth function arbitrarily well. And then also to do gradient descent in order to learn all these parameters, you need to do this chain rule to learn all those gradients through this like hierarchical structure. But the backpropagation algorithm is a way to basically apply the chain rule without repeating calculations too much. So I think it's related to dynamic programming if you're familiar with that. And so that's like a bonus in the favor of deep learning. This layered structure works out nicely for calculating those gradients reasonably fast. Okay, so those are some good things about deep learning. On the other hand, it can be tricky to use. So like in linear regression, we were trying to minimize mean squared error, which is a quadratic function in terms of the parameters we're fitting. And so it's a convex problem. There's only one optima. In neural networks, we have this very complicated function to map from input to output. So once you do mean squared error with that, you have a non-convex function. So you can think of it as like this, in that you're trying to travel down the surface to find the parameters with minimal error, but you could get stuck in these local minima. So if you imagine you start some random place on the surface, you do gradient descent to keep traveling downhill, and you might travel into one of these not so great places. So that means that how you initialize your neural network matters, and it matters, like the details of how you do the optimization matter. And so I think of this as, from the theory, we know there is a good neural network for your data, assuming your data is reasonably nice, but we need the optimization to actually find that good network, not get like stuck in one of these other spots. Now I have a math background, and I took a lot of optimization classes in the math and engineering departments, and so I think of it as you study like optimizing like different kinds of problems, you get increasingly difficult. So if you were trying to do a linear optimization problem, then you have great algorithms. If you have like a quadratic problem like linear regression, then okay, good algorithms. And as you move down to harder and harder objective functions, the actual process of finding the best parameters gets harder and harder. In these earlier cases, you spend more of your time formulating your problem to be in this category. So like if you take a convex optimization class, you talk a lot about how do you make your problem convex so that you can use those algorithms. But once you're down here, you're spending more time trying to get the optimization to find a good solution. And so deep learning is like here, we have gradients. Technically, we could get second derivatives, but often people don't bother because it's considered too computationally difficult. And so this is why we're using gradient descent. We're gonna at least make use of our gradients. And because of this non-convexity, this is why people can get, it can take a lot of attempts to get your deep learning to converge, and we'll experiment later. Okay, another downside of deep learning. So I mentioned the universal approximation theorem means you can fit these like arbitrary functions as long as they're reasonably smooth. Well, so the downside of that is that they can be kind of too flexible. And so you can easily overfit your data. And I like to think of, maybe you've seen this in the context of fitting a polynomial to your data. So here, we have this little one-dimensional data set. The blue dots are your data. And if you, in this underline orange is some like true function that was used to create this data set. If you fit a line to this, then like it's decent, but it's not really capturing the trend. This is called underfitting. Some people say it's refer to it as high bias, like the model is too biased. It's too simple. But if you fit a degree 15 polynomial to this data, it's trying really hard to match all those points, and it does crazy things in between. And this is called overfitting. So like, especially you can see right here, it's curving wildly in order to really hit all these data points. This is called high variance. And some balanced approach would be using a degree 4 polynomial, and you kind of have this balance between it's not perfectly hitting these points, but it gets the overall trend. So these pictures are with polynomial regression, but a similar, you can think of similar issues using a neural network. Okay, so I mentioned the importance of test data. It's very important that you split your data at the beginning between training, validation, and tests. So this is like one way to split it, 70%, 20%, 10%. Really, it depends on your problem. The training data is what you use in the gradient descent to fit the parameters. The validation data you can use to compare different models. So let's say we talked before about how to pick a learning rate. So let's say you try like 3 different learning rates. And like, oh, I wonder which one was best. You could evaluate those 3 neural networks on your validation data. Whichever of the 3 has the lowest error on the validation data, you pick that one. And then the test data, you should save until the very end of your project, and then check the error on your test data. And the idea is that you're able to report like how well your model generalizes. So if you peek at the test data, you've kind of ruined it. It's not really held out data anymore. And I should note that tutorials do not follow this. So as you saw at the top, we loaded the MNIST data as just train and test, and we looked at the test data because it's not a serious project. But in practice, it's very important that you set aside the test data. So for example, if you're working with some collaborators and they are like, oh, here's my weekly update on my deep learning, and they start showing you their test error, be like, wait, don't show me the test error. Now you've like contaminated it. You don't look at it till you're like ready to write the paper. Or if you're at a company and you're like ready to deploy the algorithm, that's when it's like, okay, we think we're ready. Let's check the test data to be sure. Okay, so this is very important and is like a way to get your paper rejected. I'd say like maybe 10% of the papers I review mess this up. Okay, does anyone have any questions about these ideas before we move to the next notebook?
The question I always get asked is what do you do if you get bad accuracy on your test set, if you really can't return to it without biasing your reports of accuracy?
Well, I think what I would do is like collect more data. So if you kind of get to your think like, oh, I'm ready to write the paper or I'm ready to deploy this, and you check your test data and like, oh no, the test error wasn't as good as I expected, I actually overfit, then I would try to like improve your deep learning, your method. But in order to check that those improvements, you're going to need more data. And this is kind of at a high level, similar to p-hacking. So like if you just tried like tons of stuff and something randomly works, then it's not like good results to report.
I would say that problem is pretty prevalent in deep learning, that people often will subtly tune to their and bias their results to the testing data set by revisiting it. Same thing with data pollution, where somehow they get some mixing in their testing and training data set.
Yeah, and there's some pretty like nuanced ways to not like accidentally mix up these data sets. So Kyle, if you have any examples, you want to put it in Slack, or I can grab some later. I think that's pretty interesting. And another like sort of meta problem is the machine learning community is very interested in benchmarks and like let's compare our methods on the same data set, which I think can be really good. A downside is if everyone, so take MNIST for example. We loaded it, it was built into the package, they already split it into train test. That means like thousands of people have to check that test data set. And so as a community, you can kind of overfit these test data sets. And I know people have talked about that with ImageNet, which is like a common benchmark data set that you might publish a paper and be like, oh, this is a really great approach. And like, well, that it was really great on this, like the idiosyncrasies of this exact data set and how the training data looks. Anything else? Okay. So we are ready to move to notebook 2. So I'm back on the Colab page. If you lost this, you can put in the GitHub link again. And we're ready for this one called 2 Keras. Okay, so in the first notebook, we were talking about doing gradient descent by hand, and I showed you how you could make more and more complicated models. And really in practice, we don't write out those matrix multiplications and everything by hand. There are 2 really common Python libraries that we see a lot for deep learning. One is TensorFlow, which we're going to stick to today, and another is PyTorch. Really, there are other libraries too, but these are the 2 that most of our users are using on our supercomputers. And the Keras API, well, the Keras library was originally its own package. Now it's been absorbed into TensorFlow, and it makes some of the coding simpler. So we're going to use that here. So again, we're going to import some Python packages. And again, we'll load the MNIST data set. This time we're not going to flatten it right away, but otherwise the cell is the same. And so now my training data it's still 60,000 rows, but it's a 3D tensor because each image is left as a 28 by 28 2D representation. Okay, and first we'll talk about how to implement a linear model in Keras. So this is, again, it's not going to be very accurate, but it's like a simple way to show you the library. And okay, so here we define the neural network model as a class. You don't have to do it in an object-oriented way, but that's what we're doing today. And when you feed in your input data, And first we use this flatten layer. So just for now, we're still going to flatten the images so that they're each a vector, but this time we're incorporating it into the neural network. And then we're just going to apply one layer, and that layer is defined here. They call it a dense layer. A dense layer is the basic affine transformation. So multiply by a matrix and add a vector. And then optionally, you add a nonlinearity, which is called an activation function. So here's the part where you can say that. So you can think of a dense layer as, like if we think back to that network picture, you're connecting each input to each output of that layer. So the word dense would be like, oh, all those connections are there. It's a dense matrix we're multiplying by. And this, you'll also see this called fully connected. And here I use the softmax activation because we're doing classification. So we want the outputs to be this 10-dimensional vector, one for each class. They should add up to 1. And so you can think of them as probabilities that this image is in each class. This 10 here means that we want this layer to output a 10-dimensional representation. And we didn't have to explicitly say that the input is 28 by 28 because it's going to figure that out. But basically, this is like we did in the last notebook. We're learning this A that is going to go from 784 to 10. Okay, so in this cell, we define our linear model. And then we have this compile line where we get to choose what our loss function is. This is that objective function or error function, whatever you want to call it. And we're going to choose categorical cross entropy, which I mentioned before is common for classification. And this time we used the sparse version, which you can think of as sort of handling that one-hot encoding for you. We don't need to transform our labels into one-hot encoding. It's sort of handled here. We get to pick our optimizer. For now, I'm picking the most basic version, which is stochastic gradient descent. But there are other options that are kind of like improvements upon gradient descent, but same core idea. And we're saying, oh, let's track accuracy as we go too. Okay. So this is a concise way to do the whole gradient descent method of fitting these parameters to our data. We just do model.fit. And in the next notebook, I'll show you a more verbose way of doing this, where we explicitly loop over the data, taking one step at a time. And that can be helpful when you want to do like more customized things and performance tuning. But for now, we can just do this one-liner. So we're passing in the training data. These are the images that we pass in. And remember, Y-train are the labels, the digits 0 through 9. And we mentioned that really we don't want to look at all the data at every step. So we pick a batch size. Here I picked 512. People often pick powers of 2 for performance reasons. We decide how many epochs to go. Now, an epoch is how many times you pass over the data. So one epoch is you go through all the, I think it was 60,000 examples. Oh yeah, here you go. In batches of 512. Then the second epoch is let's shuffle them and do it again. And this just controls how much we want it to print as it goes along. And so it's showing us the loss is going down. That's good. And the accuracy is going up. That's what we expect to. The accuracy is like the, if you multiply by 100, it's the percentage correct. So we're ending with like 88.6% correct. And we can also print out this summary. It looks pretty short here because we just had one layer, this one dense layer. And it says that we had 7,850 parameters to train. That's because that weight matrix was 784 by 10. 784 was the number of pixels and 10 was the number of classes. And then there was that bias vector, so that adds another 10 trainable parameters. And it can be convenient to plot. I know we printed the loss and the accuracy, but it's convenient to plot them. So we see loss going down, accuracy going up. The loss was that sparse categorical cross entropy, which is not particular, these numbers are not intuitive to me, which is why one reason you might want to print accuracy. So we see we're going up and we're not reaching 90%, and the improvement is slowing down. So again, if we thought this model was actually good, I would probably run it longer because it's still improving, but it's just a linear model, so I don't actually think that's worth it. And remember, this is on the training data. So it might be exaggerating how accurate our model is. In practice, I would also pass validation data and we could plot both. Here we're going to, since we didn't pass it an extra data set, we could check the error afterwards. And so we're checking the error on the test data. And we get 89% accuracy. So again, really this should be validation data, not test data, because you hid away your test data. Okay, so 89% is not impressive for this data set. We didn't really expect it to be good anyway, because it's a linear model, but here's an example of how we might want to investigate further, like what kinds of mistakes are those 11% mistakes. So here's a helper function that plots the first 10 mistakes. And it shows what class it predicted and in parentheses what it should have been, in case you can't tell. Some of the mistakes make sense, like I could see how you might think this could be a 4 and this one a 1, and other ones are just pretty bad. Okay, so now let's move on into a more complex model. We're going to add some another layer here. So this is our hidden layer, and we're going to use the ReLU activation, nonlinearity. And this 20 here means the first layer is going to output 20-dimensional representation. So the input is the number of pixels. This layer will transform it to 20-dimensional. And then we still have our final layer like before that will go to 10-dimensional, and we want softmax. And if you want to experiment, you could comment out some more layers to make it a more sophisticated model. This one called dropout is a common technique. Dropout randomly turns a percentage of the inputs to 0, in this case 20%. So that's kind of making your model be more robust to noise loosely. So it's like, oh, you pass through the data and a random 20% of this layer gets turned to 0. Just ignore it. And the random turning to 0 only happens during training, not when you deploy it afterwards. So this is a common technique to avoid overfitting. So you can experiment with that. Here we're again going to flatten the inputs and then apply our 2 layers. So we define our model, we compile it. Again, we're going to use the same loss function. This time, let's use a fancier version of gradient descent, RMS prop, which you can read about here. And let's track accuracy as we go. And this took a little longer. It took half a second on my laptop instead of 1/3 of a second. it's faster in the Colab notebook. And if you uncomment these layers to make it more complicated, it took about twice as long on my laptop. And at this point, you might be interested in changing the runtime to a GPU, and that really speeds this up. So I ran this for 30 epochs. We see the loss going down, we see the accuracy going up, can plot it. And this is definitely better than the linear model, but we should check it on the training data. Okay, we get almost 96% accuracy instead of, I think the other one was 89%. So again, we can check the first 10 failures to get some intuition of what's happening. And this helper function has this cool feature where you can say, oh, I want to see the mistakes on 6s. So here's the first 10 images of a 6 that the model is confused about. And so it's kind of, it's good to take a look at your data, gain some intuition. We see that there's quite a variety in how people wrote 6s. This can be a really helpful diagnostic. And another thing that could be helpful for classification is to calculate a confusion matrix. If you haven't seen this before, this is 10 by 10 because we have 10 classes. Each row corresponds to the true class, and each column corresponds to the class that was predicted. This entry here would be the number of images that are truly a 0 that were labeled a 0, whereas this row would be the number of images that are truly a 1 that were labeled a 0. And we have these big numbers on the diagonal. That means lots of correct labels. And if you see a large entry, that gives you an idea of which classes are getting confused. And we can also do some summing and get the classification accuracy for each class. And we see right now that 8s and 9s seem to be the hardest. Okay, so in this notebook, we moved to using Keras instead of doing everything by hand. And we moved to like fancier neural networks. In the next notebook, we can introduce convolutional layers, which will definitely improve our performance for images. But do people have questions before we move on? I guess I don't have the chat open. But if anyone wants to unmute.
No questions, it looks like.
Did you say no questions?
Correct.
Okay, thanks. Okay, so we're ready for notebook 3. So if you've lost it, you can go to the GitHub tab. Paste in our repo, and we want this notebook 3 Keras in it. Okay, CNNs that's short for convolutional neural network. So they have these things called convolutional layers that I'll introduce. But first we're going to start the same as before. You want to import some Python packages. Load up our data. And this time we're actually going to leave our images as 2-dimensional instead of flattening them. Okay. Convolutional layers are useful, especially for images. Let's say this is our image here, like the 28 by 28 pixels. A convolutional layer learns a filter. Let's say it's, in this example, we're going to use 3 pixels by 3 pixels. So think of this filter as a little 3x3 matrix. It's learning 9 parameters. And we do the dot product of this filter with the upper left-hand corner of your image, the first 3x3 window of your image. So you do the dot product here, and that gets you this answer that you pass on to the next layer. And then we slide the window over and do it again, filling in the output of the layer. You go across and then you go down and so forth. You can, makes some sense for images. You could think of it as like, let's imagine this filter was, let's say we were classifying cats versus dogs. And let's imagine that this filter decided to like look for whiskers. Well, we don't know where the whiskers of a cat are exactly going to be in this image, because maybe it depends on the angle of the photo. Maybe it depends on how it was cropped. We just know we're interested in whiskers being somewhere in this image. So if you imagine this filter is like a whisker detector, then we're sliding it along, searching everywhere for whiskers. And maybe it kind of gets activated or like outputs some big number when it finds a whisker. So it's not, they're not like, we're not coding that it's going to literally look for certain features, but that's kind of what you can think of it as. And we don't just have one filter, we choose how many we want. So in this example, we have a layer that does 32 of them. We have another layer that does 64 of them. So you could imagine like one filter is a whisker detector and one is looking for like a certain shape of nose. And the neural network training is choosing these weights in the filter. So again, we're not saying, oh, you should look for diagonal lines or something. But people have tried to dive in and interpret what it's learning. And there's some idea that the earlier layers in the network are learning sort of like lower level features along the lines of like textures and certain things like diagonal lines. And then the later layers are learning like more and more complicated patterns to find. In convolutional networks, there's also often these max pooling layers, and they also have a window. In this example, it's a 2x2 window, and you move along the window, and you just take the maximum value of that window, and that's what you pass on. So you can think of this as downsampling in a very simple way, just the maximum value in that window. And if we look at how we put that all together, in this example, convolutional neural network, first we have a convolutional layer. It has windows that are 3x3 that it slides along your image. It does 32 of those. And then we have another convolutional layer. It's again doing 3x3 windows, but to the output of the first convolutional layer, and it's learning 64 things. And then we have this max pooling layer, which is making our data smaller because it's doing this downsampling. It slides along this 2x2 window and takes the maximum value of each 2x2 window. So now we're up to here. We've applied 2 convolutional layers, a pooling, and a dropout. And then in this network, we're going to flatten it at this point. And we're going to apply a fully connected layer like we did before, another dropout layer, and our final layer that we're using every time for MNIST, which is that we want to output a 10-dimensional vector, and we want to use softmax so that it outputs numbers from 0 to 1 that are like probabilities of each class. Okay, I want to pause because I don't know if I explained, if my explanation of convolutions made sense. Does anyone have any questions, or maybe you're putting them in Slack? One interpretation of this is that you're saying that you think images are like translation variant. So if you had one training example where the cat is up in this corner and another one where the cat's scooted over here, then you want that answer to be the same. So you want it to be invariant to that translation. Okay, so this hopefully looks familiar. We define our CNN model. We compile it by saying we want that same loss function again. Here, for some variety, we're picking a different optimizer. This one is pretty popular. It's called Atom. And it's again like a fancy version of gradient descent. And we still want to track accuracy. And we need to add this extra dimension for the convenience of the CNN. And here's our fit function that actually does the gradient descent. So that defined our function. Here we're going to apply it. I stuck to the same batch size of 512. This time we explicitly picked the learning rate instead of just using the default. And I'm only doing 3 epochs this time because they're slower. This took 55 seconds per epoch on my laptop. It's a little faster in Google Colab. But if you switch to GPU, then you'll see a significant speed up. Maybe it's going to be slower than it was yesterday. Okay, I'm going to switch to GPU because it's being surprisingly slow. So I have to rerun these cells. These were really fast cells. So. Okay. Should be better unless I'm in some weird state. Okay, there we go. So this took 45 seconds total, and it was mostly in this first epoch, probably getting things set up, and the later ones are only 3 seconds long. And so again, we can plot the training loss and accuracy and check test data. And adding these convolutional layers definitely helped. We're close to 99% accuracy, and if you run this longer, you pass 99% accuracy. And I mentioned that this data set's been around for decades, so if you click on these links, you can see papers and how people have achieved state-of-the-art accuracy. And they talk about using neural networks, but they also talk about other machine learning algorithms. In order to kind of get an idea of how it's going, we can again do a confusion matrix. And so we can visualize that it's definitely doing better than last time. These off diagonal elements are all pretty small. It doesn't look like there's any like super common mistake. but we can also see the accuracy for each class. It looks like zeros and ones are very easy, and maybe the nines are the hardest for this network. But if any of you ran this for longer, you probably got even better accuracy. Okay, do people have any questions about this before I talk about how to do the training in a more verbose way?
Yeah, hi, I had a question just from this last part that you were mentioning. So you have some digits which are a little bit less accurate in the classification. So I was just thinking about it. Would it make sense to give the network more training of that particular digit, or would that lead to overfitting?
Yeah, I think that would be a reasonable idea, is give it more of that class. You one common problem is having unbalanced classes, so we didn't check how many examples there are of each class, but we can kind of get an idea from this diagonal that they're roughly even. So let's say we threw like a ton of nines in there, that could be bad because it gets like too focused on the nines and gets really good at nines and at the expense of the other ones. But I think within reason, it could be helpful to add more nines. And we could also, if you want to explore, in that last notebook, there was that helper function to print out the most common mistakes, including for a specific class. So we could look at, or sorry, it wasn't most common mistakes, but like the first mistakes. So we could print out, say, like visualize 10 nines that it made a mistake on and see if there's any intuition about why it's making mistakes on the nines. Is there anything that we could make use of there? And this is all like a pretty, we're just using like straightforward standard layers, but if you dive into like science domains or more complicated applications, there's a little bit more of trying to use your domain knowledge to keep improving. Does that make sense?
Yeah, it does. So basically, you just experimentally determine whether you want to provide more input of the class which is less accurate, until it leads to overfitting, right? So you just experimentally do that. There is no heuristic or there is no predefined principle on which we can just make that decision.
Yeah, I don't think there's, at least I don't know of any like a predefined principle, but yeah, just like kind of the overall idea that would make sense. You just wouldn't want to overdo it by having the data like dominated by nines. But
Yeah,
if anyone else has suggestions.
okay, thanks.
Cool. Anything else? Okay, I'm going to show you a more explicit way to do the training, and we're going to use this kind of approach for some of the examples in the afternoon where we're doing performance tuning. And when I tried this on my laptop, it was actually a little faster than the concise version. I don't know if that really carries over now that I'm in the on a GPU. At least when I didn't like get the exact timing when I tried this before, but it looked like both versions were about the same. Okay, so here we have this little helper function that's just explicitly grabbing the loss function instead of just passing it as a string. And this little helper function does what's called the forward pass. So this is, we apply the model and so this is like the current version of the model with the current parameters and calculate the loss. This is called a forward pass in contrast with when you calculate the gradients. I mentioned before that there's this algorithm called backpropagation that calculates those gradients efficiently, and it moves backwards through the layer. So This is called forward in contrast with that. And here's a helper function to do the training. And we made a separate function for one iteration. And we're using these features in TensorFlow. This gradient tape is looking at the forward pass. And so you might notice that we have not had to explicitly write out any of these gradients. And TensorFlow has auto differentiation built in. So we composed these networks of pieces that TensorFlow understands. We're using all these TensorFlow functions, and so it knows how to then calculate those gradients. So here we're calculating gradients and using them on the optimizer, which we, in this case, explicitly set. And here, this is like the core, and we have it as a separate function so that we can use this decorator and have it be JIT compiled. And here we're explicitly looping over the epochs. Remember, each epoch is one pass over the data. In this particular code, we're explicitly handling that we're going to shuffle the data on each epoch. And here we're explicitly handling that we're looping over the batches. And then package this together. This should look familiar. We define the model. Here we're explicitly picking the optimizer as a function instead of a string, and passing in the learning rate that we picked instead of the default learning rate. I'm going to pass this into our training function. And here we are using this TensorFlow concept of a data set to handle going through the data. I think that this will be brought up in the afternoon in more detail. And I'm sticking to the same batch size and 3 epochs. This was the explicit learning rate I picked. That I think was the same above. This time I asked it to print how long each epoch took. So that I think is maybe similar to what happened above when we did the concise string. Okay, do people have questions about this? Because in the afternoon, we're going to continue with the same example of MNIST with this model, but look at how to parallelize and how to profile and make this faster. Okay, so I opened Slack. I see there's questions there. This is the last of our notebooks. And so, but we have some more time. So what I would suggest is exploring how to improve this network in the notebook. So like a hands-on time. You can explore, for example, what happens if you tune the learning rate. For tuning the learning rate, I would recommend showing these plots. So you can see what happens if you make the learning rate too big, what happens if you make the learning rate too small. And you can experiment with batch size. So the batch size should affect how long each epoch takes, and it can also affect your accuracy. because if you have a really small batch, you can think of each gradient as being really noisy because it's estimated based on a really small number of examples, which you always want to balance, because the noisiness can be helpful, especially if you need to escape these like local minima. But of course, the noisiness can also be bad if you're going off in the wrong direction. You can also experiment with the model itself. So this is just one way to do MNIST. We kind of semi-arbitrarily have 2 convolutional layers, 2 dense layers, and so forth. We picked these widths of layers in these filter sizes. So if you want to experiment with that, I know that has really helped my intuition if I try messing around with these. And then we can continue to answer questions.
Thanks for this. I think I might have missed a step here. I'm wondering if it's necessary to define the actual features that you're filtering for, or if I just am misunderstanding that part.
Yeah, good question. So we do not have to define what we're looking for. And so in the process of training the neural network, it's kind of figuring out itself what it should be looking for. Now, I know that sounds fancy and like artificial intelligence. Well, it is artificial intelligence, but on a concrete mathematical level, it's fitting these parameters, which are a bunch of matrices. Does that answer your question?
So because this is labeled data, it's figuring out the 2D convolution layers that are in self-conv1 and conv2.
Yeah, when we define the network, we say we want this structure, but the parameters get initialized randomly. So maybe there's like a bunch of tiny numbers. And then as we move along with gradient descent, it keeps improving those numbers by moving in the direction of the gradient, which is the direction of steepest descent. And so it's going to try to iteratively improve those parameters. Now, other approaches to this type of problem in computer vision more generally have used more like expert defined features. And so you use your knowledge and you say, oh, I think this is sort of like a way to pre-process the data and extract out useful features and then pass that into your model. And that can be helpful. But there's some idea that deep learning can help do this for you. So there's sort of a trade-off of to what extent are you going to try to input data in like a useful representation versus letting this gradient descent improve these parameters itself. Does that make sense?
Yeah, I think so. So earlier, I think I recall an example of we're looking for whiskers somewhere in this 3D image in the search to categorize cats and dog pictures. But both cats and dogs have whiskers, so that might not be a key to mentioning two of them. It might help you look at the head, but it might not help you figure out which animal you have a picture of. Is that kind of the, so we don't have to define the feature set that we want to use to do the classification?
Correct. So maybe like previous approaches, you would have said, I know things about dogs, I know things about cats, and so I'm going to try to put those in. Like, I know I want to be looking for these shapes, but in deep learning, we don't have to do that ourselves. So we're not telling it like, oh, you might expect to see eyes and whiskers and a nose and so forth. So
Just to elaborate on this,
yeah.
like you might know like classical filters, like Sobel filters, like for detecting edges are very simple, like 3x3 filters where, you know, you have a column of +1s and then a column of zeros and a column of -1s, and if you filter, convolve that with an image, it'll detect vertical edges, I believe, and vice versa for a horizontal edge detector. And so you could think about fixing that in your first layer of your CNN here, but what's so magical, but you know, in the end is just optimization and fitting a model, is that this procedure will come up with something, perhaps something like an edge detector on its own, but even better and more targeted for the individual problem you're solving.
And so then, is there any way to find out what features were being activated, or what was?
Yeah, there's like these very cool looking visualization techniques that I can share in the Slack where you can peek into the mind of the CNN, so to speak, and you can see how this hierarchical representation gets built up.
Thanks. And has this already been extended into 3D? Like you have volumetric data?
Yeah, definitely. MRIs are a huge application of CNN's voxelized data in that sense. I know people are using it for like astrophysical simulations as well in the scientific fields. Yeah, there's tons of in movies, which is in itself a 3D representation in some sense.
Thanks very much. This is really amazing introduction for me. Really appreciate it.
This afternoon, we'll have a couple talks about applying machine learning to scientific data. So I think that'll be helpful for seeing machine learning can be used for like other tasks than just classification. Now people have gotten really creative over time. So one thing that I think is cool about deep learning is that you can customize the loss function. So it doesn't have to be something like mean squared error, as long as it's something that TensorFlow can back propagate through. You could keep adding things. And so very like open research right now is things like how do you best embed your physical knowledge? So like, let's say you want to use your neural network to predict forward in time and you think your data is from PDE and you know some things, you know, certain things should be invariant, and maybe you know like something should be conserved, and people are exploring different ways to either encourage that the network obeys that or explicitly enforce it. And this question of how, to what extent you let deep learning find good features versus do it yourself is very interesting and a lot when you start a new application area. So for example, if your input data is a bunch of molecules, then there are a lot of different ways you could represent the molecule as like a vector or a matrix to input it into your network. And the success of actually finding an accurate network can be very related to how relevant is the representation. And so I think this is, since I think of things in terms of math, I think back to this idea that, so let's say the MNIST data set, it is possible to just kind of like blindly ignore that they're images and we just throw them in there without convolutional layers, and all the layers are just dense, fully connected, and you could get quite good accuracy, but the training is much easier if you use convolutional layers, which takes advantage of the properties of images. So I like to think back to this. The universal approximation theorem would say that it is that some fully connected network exists that would do really well on MNIST without convolutional layers. But on a practical level, we need to do this non-convex optimization, and it works better when you embed that you know their images, and so you're going to have these convolutional filters sliding across. And similarly, if you had other domain knowledge that might be useful, that affects how you represent your input data. You could say, based on theory, you didn't need to represent your data in this special way, but in practice, that can make the optimization problem easier.